I had a request come in my mailbag to ask me to do a few more videos on econometrics, and one of the videos that people were interested in is basic panel data models. And so I'm going to already assume that you know everything there is to know about cross-sectional econometrics. I'm not going to repeat a lot of things. I'm kind of tired today. So I'm going to do a very quick example explaining basically what panel data models are and a couple of different ways that you can estimate them and what these coefficients are going to mean. And so basic panel data analysis, panel data assumes that you are observing the same relationship, say the same cross-sectional relationship, but you're observing the same individuals at more than one point in time. So at least 2 points in time, you see the same people, or the same states, or the same companies, or the same animals. You observe them at least 2 different points in time, and you have observations, data for the explanatory variables and the dependent variable at multiple points in time. And so, as a little example, I made up some data that I'll show you in a second here. Suppose we have a question. After teaching a class in which you give multiple tests to the same students, you might ask the question, how does study time affect test results? And that should not be affect, that should be affect with an A. How does study time affect test results? So we might want to run a model where our Y variable is test score, and that's explained with a basic linear model here where there's a y-intercept and a slope times how many hours you studied for that test. So the y-intercept would mean what's your score if you studied 0 hours. This slope would mean how much does your score go up for each additional hour that you study, times hours. Let me show you this basic data set that I just made up here in Excel. Suppose we have 4 students, Antonio, Joe, Sue, and Mark. They all took the same class, and we gave them 3 tests each in the course, 1, 2, and 3. And so for each student, we observed them 3 different times. And suppose on each test we asked them, give me an honest estimate about how many hours you studied for this test. So Antonio studied 8 hours on the first test, 5 hours on the second test, and 9 hours on the third test. And here are the test grades. Now, I actually created this data. I know what the real model is that created these answers, but I've already forgotten it. So what we're going to do is we're going to try to estimate the real model and see what happens. So let's suppose the first model we're going to estimate is just this very simple one. Now, doing this way, we're not taking advantage of the fact that we have multiple observations on the same people. We're just running a regular simple regression here. Let's bring this data into R and see what we get. So I'm going to bring it into R. I'm going to highlight this data here and do copy it to the clipboard. Then I can go into R. I'll assume that you've watched me do this dozens of times before. We can say call our data testdat equals read.dilim clipboard. Okay, so now our data is in R. Let's just make sure. Let's do a summary of the data. Whoop, I misspelled it. Okay, so the data is there in R, and it tells me it has 4 students, 3 observations each. And for the quantitative data test and study time, it gives me summary data. Well, this isn't really, it's sort of quantitative, but anyway, it's treating it as a number. That'll be important in a minute. We're going to tell it not to treat that as a number later on. But really, we want to just know how study time affects the test grade. Let's see what happens. So test reg 1 equals LM. Our dependent variable is test grade. Oh, before we do that, let me attach the data. Attach test stat. Okay, now it'll be easier for us to run a regression. Equals LM test grade explained by study time. And I will post these data in my files section on Berkey Academy if you want to download this Excel worksheet and do the same thing along with me here. So now let's see what we get. Summary of T-Reg 1. Now someone else, well, actually the same person, asked me to go through explaining tables of regression results. So in most regression results, this just describes the residuals here, the largest negative, the largest positive residual. It says that for one person we mispredicted or predicted wrong their test score based on study time by 5 points. And there was another person we predicted 5 points, but one of these we predicted 5 points over, and the other we predicted 5 points under. Our y-intercept here is 33, so that's our estimate of what would somebody score if they studied 0 hours on average. And this tells us that for each additional hour of study time, you are going to gain about 4.5 points on your test. Now I know the real model that generated the data, and I'll tell you, this isn't too far off. These results are pretty good. They're a little better than I thought they would be. Let's see if our results improve as we go along though. So our slope here, 4.5, y-intercept 33. So we could plug those in for any student, and we could generate predictions here. Now let's just take one last look here. Our r squared is about 0.94, so we're able to explain 94% of the variation just using this data, which is pretty darn good. Maybe the data I made up didn't have enough variation in it that's unobserved so far. We'll see what happens. We'll see what happens. So here we have the results that, let's see, test grade equals 33 roughly, I'll just round off here, plus 4.5 times the number of hours that you study. Now, there's another kind of model, a very common kind of model that people run when they run data analysis with panel data, and that's what's called a fixed effects model. So that's what's right here. Let me type that here so you can see what that looks like. Fixed effects model. Fixed effects model has an equation like this, where basically what we do is we add for each individual. So for each of these students here, let me bring the student data back over here. A fixed effects model would say that, you know, of course study time affects test grades. However, I bet there's something else that affects test grades. I bet Antonio, Joe, Sue, and Mark are different. They're not all don't all have the same intelligence or preparation or memory skills or previous coursework. And so I bet there's something different about these 4 people, and we should probably control for the fact that there are these differences between people. That's what's called a fixed effects model. Now a fixed effects model says, sorry for moving that unnecessarily, fixed effects model says we're going to add in this little term here, Fi, for an individual specific fixed effect. We need to build that into our model somehow to say that Joe is different from Antonio, and Sue is different from Antonio, and Mark is different from Antonio, and of course they're all different from each other. The simplest way that people normally build this into a model is just to say, okay, let's add in some number, f, that is a different starting point for each person. We're basically giving each person a slightly different y-intercept. You can also change the slopes for people. I'm not going to do that in this model, but how could we actually do that? Well, what we need to do is create dummy variables. The normal way this is done is to create dummy variables. And if you've watched my other videos, you know if there are 4 categories, 4 different students, that to represent 4 categories you need 3 dummy variables. And we could do that in this way. We could make a dummy variable to tell us which observations are Joe's, which are Sue's, and which are Mark's. We're going to leave out Antonio as the reference category. So anytime you put dummy variables into a model, you need to leave out one of the categories. Otherwise, you have perfect multicollinearity. So for these dummy variables, we're just going to go through and ask, okay, tell me with a 0 if it's not Joe, or 1 if it is Joe. So these aren't Joe. These are Joe. Here's Sue, so she's not Joe. And this is Mark. He's not Joe. Now, what you might be seeing here is that every time I hit enter, these test grades are changing. And the reason they're changing is I have a random error term that Excel is randomly updating each time I hit enter. So each time I copy and paste these data into R, we're going to be dealing with a slightly different data set. We can avoid that though. I'm going to show you a trick in R to do this automatically, to create these dummy variables for us. Sue, we would need to create a dummy variable for Sue as well, and we would do them this way. Okay, here are the 3 test grades for Sue. And we would do the same for Mark. So all 0s except for 1s for Mark. We could read this data back into our statistics program now and then include Joe, Sue, and Mark dummy variables, and that would give us the fixed effects. Rather than doing that, because that's going to change these test grades randomly, let me show you how we can do that in R automatically. And if you're familiar with R, you probably already know this. Any variable that is a word, that is a qualitative variable like Antonio, Joe, Mark, and Sue, R will automatically create dummy variables for you when you run a regression. So we don't have to worry about it. So all we have to do here to include fixed effects for the individuals, I'll give it a new name here, test reg 2 lm test grade plus another variable, student. Well, which student it is we're talking about is an important variable. Now, what just happened in R here? One second. Oh, I see what I did. I just typed the formula wrong. It should be test grade tilde student plus study time. I put the plus in the wrong place here. I apologize for that. Now let's do a summary of those and see what we get. So now when we run the fixed effects regression, we say, well, we have repeated observations for each person, so let's see how these people are different. Remember, we left out, when we created the dummy variables here, we don't have a dummy variable for Antonio. The reason I did it this way is I knew that R, when it creates its dummy variables, it always leaves out the alphabetically lowest person or thing as the category. If we had states, and this was Alabama, it would leave out the state of Alabama. Antonio, since he's alphabetically first, he gets left out. He doesn't have his own dummy variable. He's the reference category. So what these mean, what these coefficients here mean, is we've estimated now the y-intercept is 22.6. That changed a lot when we did this fixed effects model. This tells us that we're estimating that Joe is about 6 points better than Antonio, the one we left out, and that Mark is about 11.6 points better than Antonio, and that Sue is about 4 points better than Antonio. And again, these estimates, these are close to the model that I actually created the data from. Here, study time, instead of being 4.5 points per hour of study time, it's giving us 5.5 points of study time. And again, that's also kind of close to the real model. Of course, our R squared goes up here. When you add more explanatory variables, your R squared will always go up. R squared's already pretty close to 1, just like it was in the last model, without the fixed effects. So when you run fixed effects models, your R squared will always go up because you're adding extra explanatory variables. The question is often, are any of those fixed effects statistically significant? And here, all 3 of these, except maybe the last one, since the p-value is 0.06, are statistically significant. We can really say, based on this data, that Joe and Mark are different from Antonio. Sue, we're not so sure. We're not quite as sure whether she is a better student than Antonio. Now, let's go back and look here at another common model that people will run when they have panel data analysis. So this is called the fixed effects model, letting each thing you're observing multiple times have its own difference in the y-intercept. So just in case that wasn't clear what these mean, if I was predicting Antonio's score for a test that he studied 10 hours for, we would predict it this way. Antonio's score is 22.6 plus 10 times, since he studied 10 hours, 10 times 5.476. That would predict what he would score. But if Mark was taking a test, we would do the same thing, 22.6 plus 10 hours times 5.47, plus, since it's Mark, we know he's a better student, we're going to spot him an 11.64 points on his prediction, just because he always does better based on this data. Okay? And Sue would only get spotted 4 points and Joe 6.3, because all these students look like they're better than Antonio. If this was a negative, it would mean that this person is worse than Antonio. Okay. That's called a model with individual fixed effects, individual observations fixed effects. Another kind of model adds time period fixed effects. So this is called the fixed effects model, but it's individual specific fixed effects. Let me type that in. Individual fixed effects. In this model, I add in to the individual fixed effects model, I'm also adding in time period fixed effects, or in this case, test fixed effects, because what we're studying here are 3 different tests. Maybe it's possible that these tests aren't all equally hard. Maybe one test was harder than another test, or easier than another test. How could we do that? Well, we have 3 different tests. We could create dummy variables for 2 of the 3 tests. So we could create another dummy variable here called test2 to tell us which of these scores were for the second test, which were for the third test. We'd leave out as the reference category test number 1. And so we could create those dummy variables by hand. We don't have to in R. Let me show you how we can do that. In R, because, let's go back up to the description of the data, Because these tests are the numbers 1, 2, and 3, you can't just put the variable test in there and have it create a dummy variable. It would treat it like it's a number, and that's not right to do in this case. So if you want to use test to create dummy variables, to see if there's a difference between how hard each test is, we need to create another variable like this. Test dummy equals as.factor test. What this tells R to do is to create a new variable from the numerical test, first, second, or third test, and create it as different categories. As.factor says treat it as categories instead of numbers. Now we can run a third regression. This is going to be a regression with time period fixed effects and individual specific fixed effects. So plus study time plus test dummy variable. And now let's look at those results. So this is saying that the y-intercept we're estimating to be about 26. Joe is about 6 points better student than Antonio. Mark is about 10.5 points better. Sue is about 4 points better. And all these have a p-value less than 0.05 now. Study time, the estimate is closer to 5 points per hour. And test 2 looks like it was about 2 points harder than test 1. And test 3 looks like it was 3.5 or 4 points harder than test 1 was, because these dummy variables will compare back to test 1. The difference between test 2 and test 1 is not statistically significant. Now again, that could be for one of two reasons. Either our sample size isn't big enough, there's multicollinearity, or just the difference between the average score on test 2 and test 3 isn't big enough to be sure that this isn't zero. These answers are getting pretty close to the actual model that I use to create these data. Let me bring that model in and show you how these things compare to what these estimates are. Now again, I just created these data very simply, real quickly without thinking a whole lot about it. Okay, okay, there they are. Bring that in so hopefully you can read that. So here's how I set up the true model. I said, okay, give each student a score where the y-intercept is 28. Our estimate is about 26, so that's pretty close. Plus 5 times the hours studied was used to generate this data. So that's here, study time, 5.3. That's pretty close to the actual model that created it. Plus a student fixed effect, where I created those fixed effects where Sue was 4 points better than Antonio. 3.92, that's right on how I created the data. Joe 5 points better. Joe 5.7 points better is our estimate, that's pretty close. Mark was 10 points better. Our estimate's 10.6. And I also made the second test 2 points harder than the first test. And that's what our estimate is, right at -2. Let me bring back up the real model here. And R. And I made the third test 4 points harder than the first test. Our estimate is 3.6. So these estimates are pretty close to the way I created the data. Then when I created this data in the Excel spreadsheet to get these test grades, I just added on a random number. And as you've been seeing, these test scores update every time I enter something and hit the enter key. Again, let me just say a couple more things about panel data analysis. With this data that I created, we had 12 observations. We have 4 subjects, 4 students, times 3 tests gives us 12 observations, 4 times 3. Whenever you do these various panel estimates, whether you have individual fixed effects and or time fixed effects, you have to watch out for your degrees of freedom. Now remember, degrees of freedom is equal to, let me make this a little bit bigger so we can actually see it. Degrees of freedom is equal to n, sample size, minus k, number of explanatory variables, minus 1. And so in this case, we started with 12 observations, minus, and our final model here we have 1, 2, 3, 4, 5, 6 explanatory variables, minus 6, minus 1, degrees of freedom, only 5 degrees of freedom in the model. Remember that the more degrees of freedom you have, it's going to make your estimates more accurate. It's going to lower those standard errors, and also it's going to help bring your p-values down because your t-distribution is going to get closer to being a normal distribution. So when you don't have a lot of degrees of freedom in a model, don't be surprised when some of your variables aren't statistically significant, even if you know, like you're creating example data like I am. So this is a worry sometimes that when you put in fixed effects for each individual and time period fixed effects, a lot of time, even if it's proper, even if it's the right thing to do, it can, I want to say mess up, in quotation marks, mess up your answers, mess up your results for a couple of reasons. Number one, sometimes the individual and time specific fixed effects absorb so much of the variation in the data that the variables you want to investigate, there's just not a whole lot of variation left for the other variables to explain. That's the best way that I can help try to explain that. And a second thing is sometimes you don't really have enough observations to support adding all those individual specific and time specific fixed effects without eating up all of your degrees of freedom. So sometimes, as in just about every case in econometrics, you have trade-offs between doing the right thing that you think really is the best way to model the data and doing what your data can actually support based on how many observations that you have.